Alright, hell yeah. So we're going to go over multivariable calculus. This is a textbook that I picked up, just a PDF online, you know what I mean? It was just a download. A lot of these you can get for free. Now, I do have almost the same book in front of me. I have the 6E edition, because I can get those for like 10 bucks, you know what I mean? So that's kind of what I'm willing to spend on a textbook. But hell yeah, I just wanted to go over, so this is kind of probably a pirated version, but hell yeah. What I want to go over in this video is like how to read a textbook. So we're just going to page down and get to the first problem, or just kind of like the first. Here we go. So you know what I mean, the first sentences, and this is really important. So what we also have is Google open for us, and what we're going to do is we're going to read, and then anytime that we get to a place where we're just like, oh, you know what I mean, I don't know what's going on, we're just going to kind of Google AI it. So let's see how we do. So we have parametric equations and polar coordinates. It says, so far we have described plane curves by giving y as a function of x. And so even, you know what I mean, hell yeah. So we have equations that are y as a function of x. I can keep up with that. We're going to put them in the form of y is equal to f of x. Okay, hell yeah. And I can even... yeah, you know what I mean? Sometimes you write it as y, sometimes you just say it's a function of x. And we're going to take x, we're going to add this number to it, and that's going to be y, you know what I mean? And so, or x as a function of y, where we can actually have x over here, and then you can have gy over here. And now, you know what I mean? This is where it's just like, well, I've never done that before. So you saying that if I have f of x is equal to, something something x, then I can have, I wouldn't call it f of y is equal to something something y. I'm going to say it's a different function. I'm going to say it's g of y. But these letters are just arbitrary, so let's continue on. So it says, or by giving a relation between x and y that defines y implicitly as a function of x, where you write it like this. We have a function of x and y, and that's going to equal 0. And so that's kind of interesting. And that's where I kind of went to Google AI and said, well, let's, I guess, read on just a little bit. So in this chapter, we discuss two methods for describing curves. Some curves, such as the cycloid, are best handled when both x and y are given in terms of a third variable called t. And t is called a parameter, where you have x is a function. So where you have a function, you have the function of a parameter is equal to x, and you also have a function of this parameter t is equal to y. So we have x is a function of the parameter, and y is also a function, a different function of that parameter. So other curves, such as the cardioid, have their most convenient descriptions when we use a new coordinate system called a polar coordinate system. Hell yeah, and just the other day I kind of read this first, little paragraph, and I was like, you know what I mean? I said this, if I have f of x, then g of x is the next one h of x. I just wanted to know, and so hell yeah, it's going to say this statement, if f of x then g of x is the next one h of x, is not a standard mathematical expression. Oh, see, I didn't really like that. But it says, it gives you some examples when h of x would come up. If I have f of x and g of x, and then I'm going to relate the two, we have this third parameter called h of x. And then I Googled it, is the next one, the next one I of x. And it probably freaks out again. Yeah, and so basically, and then whatever letter is clever to you when doing that. So that was just kind of one of my strategies of just like, well, you know what I mean, is this f set in stone? No, it's just a variable. Just this x is a variable. You can change that letter to anything. Cool. All right, and then, but this implicit, I think I had a question on there. I said, if a function is implicit with x and y, can it not be solved for y? I was just curious about that. And it says, well, it says yes, some. It says yes, some implicit functions involving x and y cannot be solved for y to express it explicitly in terms of x. And this gets me thinking as well, because you have mx plus y is equal to mx plus b. So I'm going to say, and then this is crazy. YouTube, Yahoo, they pirated my, it's a virus. Whereas every time I pop it up, it goes to Yahoo, and it's the worst search engine in the world. I still use their mail, but their search engine just sucks. And I don't know if it's them that pirated that, but holy Toledo, I got to type Google in every time. Okay, hell yeah. So I'm just going to look up, so we have y is equal to mx plus b. So I'm going to say y minus mx, I guess we don't have to get into all caps, y minus mx minus b is equal to 0. And I'm going to ask, is this an implicit function of x and y? Oof, typing. And and it says, I don't know. Let's see what it says. An implicit function is an equation where the dependent variable is not explicitly expressed in terms of the independent variable. So sometimes you have to Google all the way down. Right here, the equation is an explicit function of x and y, not an implicit one. Whoa, okay. So I'm gonna write, because I didn't think that was gonna be the case. So I'm gonna say, if a function can be represented as solely, I don't know how do you write that, as a function of x, function of y, is it therefore not implicit? When a function is explicit, it means that one variable is clearly expressed in terms of the others. For example, you have a function where y is isolated on one side, is considered an explicit function. An implicit function, on the other hand, is where one of the dependent variables is not isolated on one side. So for instance, x squared plus y squared is equal to 1 defines y implicitly. And then so let's, what is an implicit function of y and x that can be expressed explicitly as a function of y? All right, hell yeah. An implicit function of x and y like this can be expressed explicitly as a function of y. But just know that y is going to be plus or minus the square root of 25. However, some implicit functions like this one, oh yeah, so if you have like a y to the cubed, and then on this side you also have an x and y, or even, in various things like polynomials. It cannot be expressed as well. It's just this example makes sense to me, I guess. Yeah, it cannot. It's going to be very difficult to express or impossible to express as a function of y. Cannot explicitly be expressed as a function of y. So now I'm going to say, can y is equal to mx plus b be written implicitly? And yes, the equation y is equal mx plus b can be written implicitly. The implicit form, so that's why using this is because it says like, hey, the the equation, this is an explicit function of not an implicit one, but that's not true because look at this. So sometimes Google AI kind of gets it wrong because it just says that the implicit form of this, the implicit form is written like this. You have ax plus by plus c. And so there you go. So by is 1, and then ax is going to be negative mx, and then c is going to be negative b. And so, hell yeah. So there you go. So mx minus y plus b is equal to 0. So while y is equal to mx plus b is the standard explicit form, showing y as a function of x, you can represent the same line implicitly with equations like mx minus y plus b is equal to 0, or mx minus y is equal to negative b. And this is kind of the form that we wrote it in. We just said it was going to be y minus mx minus b. And so we didn't write it wrong because we said y is equal to minus mx minus b. It's just sometimes Google AI isn't the best. Okay, so hell yeah. So that's kind of where I got on this, you know what I mean? And so that was just kind of reading the first, and this could be whether it's the first chapter or whether it could be anywhere in a textbook, you know what I mean? Just to use this idea of looking up the terms on Google AI, and we can just read just a little bit more. But yeah, that was kind of it. That's what I wanted to make a video on. But let's read a little bit more. So we have curves defined by parametric equations. So imagine that a particle moves along this curve. And I've already kind of read this, and they're going to be like, you know what I mean? It can't be expressed in a linear way. It's not a linear equation, but we can see that this particle could be a function of time. At each individual time, it's going to be somewhere along this path. And that's also, if you've read a textbook through once, you know what I mean, try to read it again where you're just kind of imagining where they're going. So hell yeah. So imagine that a particle moves along this curve C as shown in figure 1. Always go to the figure, take a look at it. It is impossible to describe C by an equation of the form as y is equal to f of x. And do I like the way they even wrote that? Y is equal to some function of x. Oh yeah, so that jives with me. So y and f of x, that was interesting, because y and f of x are the same thing. Oh, this is bizarre to me. But then this is a complete statement. You're saying that this function y, or y is, you know, taking x and doing something to it. And I use this idea of saying like something something, because that's where you can write it in a closed form solution like this. I can write y on one side is equal to some sort of mathematical operations. Maybe I take x and multiply by 2, add 1, you know what I mean, and then square that. You know, so it's still doing something with this value of x. And in that, every other thing in this equation is just a constant. There's going to be, the way it's written in here, there is no changing variables. And maybe we can even, we could even Google that right now. So I'm just going to Google, because I think that's a case. So if something is written as f of x, let's see, does that mean that all other variables in that expression, is that how you call it, expression, because it's not an equality yet, expression are constant? Yes, when an expression is written as f of x, it indicates that the x is the variable and all other symbols in that expression are treated as constants. So this is probably the second like aha moment of doing this process of reading textbooks. You know what I mean? You have your whole education behind you. You know what I mean? But it gets scrambled. You know, one teacher says one thing and the other teachers say another. And honestly, when you get to college, it's more about getting the answers in the back of the book. You know what I mean? Especially in engineering. The answers in the back of the book are numbers that are to 3 decimal places. That's the only understanding. That's their main check to know that you know what's going on. is if somehow you can get those. And that's fine, because like that brings up concepts of like, I really would love to take a college course on, not like, what am I trying to say? Like the units are the equation. That's one way I express it. My brother said it's, I can't think of the term, but it's where it's like your units have to match up. You know what I mean? And if you, anyway, so, hell yeah, there's a lot of ways to go about learning. It can be sometimes just follow the numbers, you know, what's being multiplied. And in this case, I just use that assumption that if I have a function of f of x, what am I not going to have? You know what I mean? And so I always take things to kind of the extreme of like, what could you have and what could you not have? And this function is a function of x. It can't include the y term over here, else it would, you know, you would, or a t term, can't include that because it's just a function of x. All right, let's read on. Let me get some water. And these are so interesting because I want to do more videos like this, but also I have to kind of get good at whatever format I'm doing. So might as well just make them and just see how they turn out. Okay, so because C fails, yes, this path of C, it cannot be, yes, impossible to have this form because C fails the vertical line test, which is one of those tests that we probably all knew from high school, but just vaguely know. Anyway, but the x and y coordinates of the particle are a function of time. So we have, so here it is. So here, this is fascinating to me, because this x coordinate and the y coordinate, see now this is fascinating to me, because like we said, if this is a function of x, this can't be, any part of this expression, everything else has to be a constant. But now we can say that this value of x right here is, and this value of y, like these are not just, I mean, it's a point on here, but we're going to say the first one, we're going to say x is a function of time. And so as this particle moves to here, I know that, and if I just paid attention to the x direction, it went to there and then it went back. So as a function of time, this particle is going to go to here, and then it's going to go to there. And then so I can represent the position, the x position of this particle. And if I say this particle is going to go from there to there to there, you know, let's represent it just on this x-axis. It's going to go there to there, and then it's going to go all the way back to there, and then it's going to go all the way back to there. So x can be represented as a function of time. Now the y direction, hell yeah, we're gonna, maybe if we're starting here, I'm gonna start here, I'm gonna go down, so like I'm gonna go down in the y direction, up in the y direction, but then down in the y direction, and then back up, maybe down a little bit, up and then down. So let's represent that. I'm gonna go down, and then I'm gonna go up to that point right there, and then I'm gonna go down to that point, and then I'm gonna go up to probably this point, and I'm gonna go down just slightly, then back up, and then down again. So y can be represented as a function of time. Now, we're going to use this f of t to represent the function of time, because we're going to take the time value, maybe multiply it by 2, maybe add 1. But maybe this value is going to be multiplied by 2 and subtract 1. I mean, there's a chance that these could be the same thing. Maybe we have symmetry, where, you know, the path of this particle is just symmetric about the x and y. And that would also be if these two equations are similar, you know what I mean, but they could be drastically different. And one could just be 0. You know, the x, if the y position, if the g of t is always 0, then the particle just moves along the x-axis. But it can do this along the x-axis. It just does not move along the y-axis. So hell yeah. Okay, so that was pretty good. All right, so we can represent the x position as a function of time and the y position as a function of time. Such a pair of equations is often a convenient way of describing a curve. So that's figure 1. Parametric equations. Suppose that x and y are both given as functions of a third variable t called a parameter. By the equations, x is a function of t and y is another function of t. This is going to be f of t, and this is going to be represented as g of t. which are called parametric equations, each value of t. And so we're going to input, we can put different values of t in here, but that's not going to be, but if I say that if I put the same value of time in both these equations, that's going to be where the position of the particle is. If I say the value of time for this equation is 0, and then the value of time for this equation is, let's say, 1 second, and it gets to here in 1 second, well, then the value, if the x position where the function of time is 0, I'm just going to be, this x value is going to be right there at 0. And if I throw in this equation, if I put this equation where g of t, where t is 1 second, and I think I'm going to be up there, then this y value is going to be that height. So only if the time values are the same, then that represents that point. But that's a good way to, also. So you don't have to have the time values be the same, but if these time values are the same, that's going to represent that point. So each value of t, and so they didn't really explain it like I just did, but they do say each value of t, if t is the same number for both these equations, determines a point xy, which we can plot in a coordinate plane. And that's going to be a point on that curve. More water. Hell yeah. All right, so as t varies, the point xy is equal to, and then, so I have x comma y, that's going to be the point, but I said x is this function of time, y is that function. It's just kind of a I've never actually written anything in my life this way, but there you go. I think I can manage that. That's the other thing, is just like, one is if you don't know what they're actually trying to portray in a textbook, that's one thing. But if you know what they're trying to portray, but you're just lazy like me and like don't want to, it's like I don't even want to do that. I don't know. I think that's something that I need to get over and be like, nah, I could write it like this, and I probably should. For a few times. All right, so as t varies, this point will vary, and it's going to map out that line, and hell yeah. So varies and traces out a curve, and that curve is going to be called the parametric curve. I can keep up with this, hell yeah. So the parameter t does not necessarily represent time. Cool, and then so they're just saying that. We just showed that it could represent time, doesn't have to. The parameter t does not necessarily represent time, and in fact, we could use a letter other than t for that parameter. But in many applications of parametric curves, t does denote time. And in this case, we can interpret xy as a function f of t, g of t, as the position of a moving object at time t. And so that's what we explained, if time t is 1 second, it's here. Maybe at 2 seconds, it's here. 3 seconds, it's there. Cool. And we can map out that. Hell yeah. Example 1. Sketch and identify the curve defined by the parametric equation. So anytime I see an equation, I like to just throw in 0. So I'm going to throw in t is equal to 0. Again, it doesn't have to represent time, but let's make it. And so I'm going to throw in t is equal to 0. So 0 minus 0, 0. Then I'm going to throw in 1. Okay, when t is 1, I'm going to have 1 minus 2. So I'm going to have a negative 1. Okay, hell yeah. Now I'm going to do the other thing. I'm going to go negative 1. Negative 1 squared is 1. And then negative 1 times 2 is, minus is going to be plus. So we got minus 2 times negative 1 is going to be plus 2. So I have 1 plus 2 is 3. So at negative 1, I'm at 3. Cool. And then, so that's negative. I'm going to be at 3. Position of 3. In the x direction, at negative 1 second, I'm going to be at 3. At 0 seconds, I'm going to be at 0. At 1 second, I'm going to be at negative 1. At 2 seconds, so we're going to have 4 minus 4. So I'm going to be at 0. So at 2 seconds, I'm going to be at 0. And then I'm going to go 2, 3. So I'm going to go 9 minus 4. I'm going to be at 5. And that's what we should see. So this t is equal to 3. This is 5 in the x direction. And this value of negative, is that right? I mean, did I do that right? 3 squared is 9 minus, oh no, and it's minus 6, so that is 3. Yep. And then so, yeah, my bad. And then we started with negative 1. So negative 1 is negative 1 is 3. And then we're going to go at time is equal to 0, we're 0. At time is equal to 1, we're negative 1, 2, and then 3. So that's just following the x direction. If we do the same for the y direction, let's throw in this negative 1. We're going to have a y direction of 0. So, so when time is negative 1, oh yeah, right there. It's kind of hard for me to see, but you know, in the y direction, it's at 0 in the y. Yep. And then when we throw in a time value of 0, then we're at a y position of 1. When we throw a time value of 1, we're at a position of 2. And when we throw in 2, we're at this position of 3. 3, we're at a position of 4. And time is equal to 4, we're at that position of 5. Hell yeah. And then so what they did for this graph is they started with negative 2. And that's a good thing, you know what I mean? If anytime that you get equations, especially with parabolas, I like to use the negative 1, 0, 1 method. But then also, you know what I mean, negative 2, negative 1, 0, 1, 2. It's very easy to put those values in. And then also maybe negative 10 and then 10. Because if I throw in a negative 10 here, that's going to be 100. And then I'm going to have 100 plus 20. So that's 80. So I'm going to be 80 in the x direction at negative 10 seconds. And then how about positive 10? That's going to be 100 minus 20. Oh, no, I didn't do it right. So putting in a negative 10 here is going to be 100, and then we got plus 20. So my bad. So I'm going to start at a position of 120. At 10 seconds, it's going to be 100 minus 20 is 80. So there you go. So that kind of fits what I do when I see, quadratic equations, even cubic equations, any polynomial. I kind of use this because it's because they're not linear. You know what I mean? It's kind of nice to kind of play around with the numbers and what you can do with especially quadratic numbers is that you can see that they'll be, like, hey, this is positive x, and then we went to negative, and then we went to positive again. Or we went to a big number, we went to a smaller number, and we went to a big number. And then so you kind of, you can feel out that process. And so in this case, if I threw in a negative 1, then I'm going to get a positive number. If I throw in 0, I get 0. And then if I throw in 1, I'm going to get a negative number. Oh, yeah. Sorry about that. Yeah, there wouldn't be any change there. But yeah, you're looking for, yeah, I guess, how would you say that? Well, if I threw in 0, and then I threw in a negative 1 here, and got a negative 1, and then threw in 2, and got 0 again, then my numbers went from 0 to negative 1 to 0. And then so I know that this parabolic shape has to exist, because a straight line can't go through those 3 points when you have that. Okay, hell yeah. All right, because sometimes, like, you're not going to have a picture. You're just going to have this equation, so it's good to actually just throw a couple points at it. And if you throw a couple points at it, I think it's going to be better than just graphing in your calculator. The second you see every possible combination of points, I don't know, like, you lose a little bit of that exploration. Cool, so the solution. So it says sketch and identify the curve. So each value of t represents a point on the curve. So if I throw in this value of t, I'm going to find the x and y values from these two equations, and that's going to be a point. So I see 8 and negative 1. Hell yeah, I'm going to go over 8, down negative 1. And that's going to be negative 2. So if I throw in negative 2 here, I get negative 1 in the y. If I throw in negative 2 here, this goes to 4 plus 4. I did that wrong. So negative 2 squared is going to be 4. Minus, yeah, 4 plus 4. It's 8. Sorry about that. It drives me crazy all the time, negative signs. Hell yeah. Okay, so I think we're going to move on. So a particle whose position at time t is given by the parametric equation moves along the curve in the direction of the arrow. And so they say as t increases, this is the direction that they're going to say, a particle. So if this is representing a particle, its position as time is given by the parametric equations, moving along the curve, and we're going to put some arrows on it, in the direction of the arrows as t increases. Notice that the consecutive points marked on the curved paper at equal time intervals, but not at equal distances. So it says, note that the consecutive points marked on the curve, so there you go. So this is these are equal time intervals. So it took 1 second to go from there, another second to go from there, but the distances are not equal. Cool. That is because the particle slows down and speeds up as t increases. It appears from figure 2 that the curve traced out by the particle may be a parabola. In fact, the second equation we obtain, t is equal to y minus 1, and substitute into the first equation. So let's look at these from an equation-based standpoint. Both of these are functions of t. I can solve each of them for t and then sub it into the other equation. And so I can solve this one for t. That's going to be y minus 1. And so everywhere where I see a t here, I'm going to put a y minus 1. So let's see if we can do this mentally. I'm going to have y minus 1, and then multiply a 2 through. That's going to be 2y minus 1. And then multiply a negative 1 through. It's going to be a negative 2y plus 1. So I have negative 2y plus 1. You know what I mean? And that's as far as I can do mentally. So then we're going to square this. I'm going to get a y squared term. I'm going to get a positive 1 term, and then a negative 2y. And that negative 2y is going to add to another negative 2y. So it's going to be negative 4y. This 1 is going to add to that 2. We're going to get 3. So this is x is a function of y. And since the x is equal to y squared minus 4y plus 3 is satisfied for all pairs of x and y values, and you can see this is very similar. This is where, like, I need to see the aha moment. I mean, this is totally, if I change the x and y variables, if I said y is equal to x squared minus 4x plus 3, hell yeah, that would be a quadratic in, a vertical quadratic equation, or parabola, or however you say that. But because it's this way, hell yeah, you know what I mean? It's x is a function of y. And so, hell yeah. And that's going to be the direction of it. So if it was this way, you know what I mean? Y is in the vertical direction. If it's this way, x is still in the vertical direction. So this is an x is equal to a quadratic equation as a function of y. Hell yeah. So I can see that, and that's useful. Because I think that is one of the hardest things, is to take an equation and then be able to, put it on its side. Like, how would you do that? How would you represent this equation? Well, you could first just represent it as if this was the y-axis and this was the x-axis. Even that's a little bit hard, because if I actually did represent that, I'd want to have this, if I have my vertical axis positive, I kind of, always want this positive axis going this way. So I would have to tip this up and then flip it so that my positive axis is going this way. All right, hell yeah. But yeah, we get this equation, so what? Let me get some more water. And it says, and so the parametric curve coincides with at least part of this parabola. Cool, because t can be chosen to make y any real number. We know that the parametric curve is the entire parabola. Oh, that's interesting. I didn't really get that statement, but it says, so the parametric curve coincides with at least part of this parabola. Because t can be chosen to make y any real number. Oh yeah, so there is. So you might get this equation, but yes, because your equation for t, or if we, how do we say this? Or what did they say? They said y is, where do they even do that? Yeah, right here. So we have t is y minus 1. And so y is going to be t plus 1. And then so can we get every function of y? Because if we're saying this is our equation, that I can input any y and get any x, well, that's not the initial input. The initial input is some sort of value t to get y. So rearranging this equation for also y, so y is equal to 1 plus t. And isn't that our original equation? Yeah, y is equal to t plus 1. And then so I can get any value of y in this. But if you solve for a, if you do this method of solving for the parameter t and then getting the equations, and this would be an explicit form of the equation, I guess, of these two equations, then, there might be equations where if t varies from, even negative infinity to infinity, it's still not hitting all these points. Because maybe t is y squared. So if I throw in, or let's say y is going to be t squared. So if I throw in a negative 1 second, I'm going to get a positive 1 y value. If I throw in negative 2 seconds, I'm going to get a positive 4 y value. So then you might not be able to hit all points. And so I think, is that what they're going to show here? It is not always possible to eliminate the parameter from parametric equations. There are many parametric curves that do not have an equivalent representation as an equation in x and y. Okay, hell yeah. And so in example 1, we found a Cartesian equation in x and y whose graph coincided with the curve represented by parametric equations. So that process, or this process, is called eliminating the parameter. It can be helpful in identifying the shape of the parametric curve, but we lose some information in the process. The equation in x and y describes the curve the particle travels along, where the parametric equations have additional advantages because they tell you at any given time where the particle is. They tell us where the particle is at any given time and indicate the direction of motion. Because if you know where the particle is, and then you also know the next place that it's going, then you know the direction of motion. And that's probably due to derivatives. If you think of the graph of an equation in x and y as a road, then the parametric equations could track the motion of a car traveling along the road. No restriction was placed on the parameter t in example 1, so we assume that t could be any real number, including negative numbers, but sometimes we restrict t to lie in a particular interval. For instance, the parametric curve from 0 to 4 seconds is represented here. And so this might be, especially in physics, this might represent parabolic motion is usually, projectile motion with gravity. Throw something up and it comes down. You know what I mean? And even if you just throw something up and it comes down, that's going to map out its height in the y direction and its distance in the x direction. If you're on top of if this is the top of a building and the down is the positive x direction, this is the bottom of the building, and you throw something straight up and right up the lip of the building, and then it falls down to the bottom, that's going to be the time it takes. And this graph represents the height in the y direction and the height in the x direction as a function of time. Cool. All right, so but sometimes we restrict t to lie in cool. Yeah, let's read it. And then the interesting thing about this, because in kinematics, Like, this is such a good graph to do, because you're going to get something where, like, x is a function of time and y is a function of time. If you put those two parameters together, this, and even though it's a building on its side, and we did that example, this is the actual path. That's not the actual path seen by the particle. Yeah. Yeah, because I could throw something directly up and then directly down, and the actual path of the particle is just in a linear straight line. But this shows the height as a function of time. Yeah, that's interesting. So I don't know if I'm 100% right on that. Okay, so shown in figure 3 is the part of the parabola in example 1 that starts from point 0, 1 and ends at point x is equal to 8 and y is equal to 5. The arrowhead indicates the direction in which the curve traces as t is increased from 0 to 4. So it says as t goes from 0 to 4, this arrow represents that direction. In general, the curve with parametric equations, x is a function of t and y is a function a function of t, represented as x is f of t and y is equal to g of t, where you have this interval t is from a to b, where t is greater than equal to a, and then less than or equal to b, has an initial point fa GA and a terminal point FG BG. Cool. And we'll probably do one more and then be done with this video. So it says example 2. What curve is represented by the following parametric equations? We have x is equal to cosine t. So let's just pick our particle. So at time is equal to 0. Our particle is going to be at 1. At time is equal to, and this is going to be in radians, so if I say time is equal to, and it's kind of interesting with this, because it's just like we represent cosine as a angle, but I guess it's so fascinating to actually represent this as a value of time. Because if a spinning wheel is spinning, like I'm here, and then I'm there, and then I'm there. So if a spinning wheel is spinning at a constant rate, you know what I mean? Like I know that I'm going to be at these different points, but still, as a function of time, that still means that I'm kind of moving along that line. And so, I have a tangential velocity, and this curve has a distance, which is the circumference of this circle. You know what I mean? So always think of a circle having a circumference and then you moving a proportion along it. And you can move all the way around it and multiple times. And so, you know what I mean? If I know that I have some velocity, or if this spinning wheel is spinning, and I know if it takes me like 1 second to get to there, cool. Hell yeah. Then I'm going to be at this position, where x is equal to 0. They're going to say for this equation, that's not, if you had to do that, if at 1 second you were where x is equal to 0, the cosine, you would have to put, 1 right here, but the cosine of 1 ain't going to give you 0, so we would have to have 1 divided by, and you could do 1 divided by 90 degrees, or you could do 1 divided by, or how would you do that? Time is equal to 1. I'm kind of blanking. Yeah, circles are hell. Anyway, so if this value is 90 degrees, sometimes if you're not too familiar with radians, it's better just to throw in, 90 degrees. So when time is equal to 90 degrees, which we're saying is pi divided by 2 radians, but we should at least, anytime the word radian comes up, like what's the fastest way to get there? I'm still a slow process to be like, what the hell's a radian? But a radian is an angle. So any circle will have a radius. Cool. And then if I cut a string to be that length, I'm going to drape it along this circle, and I'm going to get about to there, about 60 degrees. And I can have each of these cut lengths of string go all the way around, and it's going to take about 6 of those strings, but 6.28 or 2 pi lengths of those radiuses to go around. And does that make sense? I think in 8th grade we always thought a circle was pi d. That's the circumference of a circle, is pi times d. And I think it gets lost that the circumference of a circle is pi times 2r. And if you say it that way, I think it might be a little more helpful, because you said the circumference was pi times the diameter. The diameter is just 2 times the radius. So we have pi 2r. So pi 2r is this circumference. And so if I have, and if I get a quarter of the way around, that's going to be pi 2r divided by 4. And so the 2 and the 4 make a 2 on the bottom, and then I'm just left with pi r divided by 2. And so, so that is the distance. So this would be the distance, pi r divided by 2. But we do define that angle, because we just said that if I cut a string of this radius and I get to here, drape it around the circle, I'm going to call that 1 radian. And so, yep. And 1 radian is where I cut the length of the radius and drape it to there. So how is that related to the circumference? Well, again, it's going to take 6.28 radians to go all the way around. So if I have, what's 360 degrees of a circle? It's going to be 1 radian times 6.28 of those. So it's going to be 1 times 2 pi, and that's the angle of a circle, which is 2 pi radians. And so if that's the angle of a circle, it seems like they made radians, and it makes it simpler, but also it makes it more confusing at the same time. Because what we're assuming also is that 1 radian is where you take this radius and drape it along the arc of a circle, and you get to there. So 1 radian is just this angle, but if you multiply that by the radius, that is going to be this arc length. So radians times radius is this arc length. All right, hell yeah. Have I just thoroughly confused myself? So the radians of a circle is going to be 2 pi radians. So, and that means that the arc length of a circle, because I think people can do like, hey, this is 1 radian, and that radian times that radius is that arc length. Well, do the radians of a full circle. So the angle of a full circle, 360 degrees or 2 pi radians. And we said, damn it, need more water. We said that radians times radius is arc length. So the circumference of a circle, or the arc length of a circle, is radians times radius. It's 2 pi radians times that radius, and that's going to be the arc length. All right, hell yeah. And then so, so what would we, what are we doing? Hell yeah. And then so I guess, by tables, or, sines and cosines, cosine of 0 radians is going to be 1, and cosine of 2 pi radians, pi divided by 2 radians is going to be a value of 0. Anyway, so I think I explained enough, but I'm sure I'm missing the actual bring it back home. Anyway, so if I throw in pi divided by 2, which is 90 degrees, and we know that a circle is, I think that's the kicker, even just the first kicker, is that radians are degrees. It's a proportion. It's the same thing. It's the angle of a circle. So I can have 2 pi radians is 360. degrees. Those are equivalent. I can have pi radians, that's 180, and I can have pi divided by 2. So if t is pi divided by 2, then this value is going to be at 0. If it's pi, it's going to be at -1. And if it's 3 pi divided by 2, it's going to be... if it's pi at 0 again, the x value... No, I'm sorry. Yeah, if the x value goes from 1 to 0 to -1, back to 0 to 1. The y value goes from 0 to 1, back to 0 to -1, back to 0. Okay, hell yeah. So if we plot these points, if I throw in the value of t from this parameter from 0 to 2 pi, then if we plot those points, it appears that the curve is a circle. And we can confirm this by eliminating the parameter. How do we eliminate that parameter? Yeah, that's fascinating. We would take the inverse cosine of both sides. What's their process of eliminating that parameter? They just say x squared. So this is equal to, because x squared, this x squared plus y squared is cosine squared t plus sine squared t is equal to 1. And they're going to say because x squared plus y squared is equal to 1 is satisfied for all pairs of x and y values generated by the parametric equation. The points x and y move along the unit circle. I don't know how exactly they eliminated the parameter, though. How do you solve for this and then throw it into the other value? That's interesting to me. I don't see it 100%. Yes, that's interesting. Oh, they're going to do it from this perspective, that if this identity exists, from trigonometry, that x squared plus y squared is cosine t squared plus sine t squared is equal to 1. Yeah, and this t is usually represented as the angle, and we just said that time value is represented as the angle as well. For this, the time value is also represented. So whatever this path of the particle, the time value is the angle as well. So that's kind of interesting. And if you threw some constants in here, the time value, like the angle, how would I say that? Yeah, I guess if it moves along a circle, the time value is directly proportional to the angle. In this model, it doesn't have to be. You could have time is equal to 1, and the angle is damn it, I don't see that either. Anyway, so if you do have this identity, and this is our x value, and we throw it into this equation, so we have cosine t is equal to x, we have x squared, and then this is sine t into y, throw it into this equation is y squared, then we do have this representation. And so, in eliminating the parameter, says x squared plus y squared is equal to 1, and therefore we can solve for y. It's going to be positive and minus the square root of x squared, 1 minus x squared. So if I get this x squared over here and take the square root of it, I'm going to have the square root of 1 minus x squared. And because I have the square root, I have the negative and positive roots. This would be the positive root, and then this would be the negative root. Okay, hell yeah. And then so that's going to be that example. So notice that in this example, the parameter t can be interpreted as the angle in radians shown in the figure 4. As t increases from 0 to 2 pi, the points x and y is equal to cosine t sine t, moves once around the circle. And then so if we have so at time t, if we're there, the x direction and the y direction, it's going to be this right triangle. And so the hypotenuse is the radius of the circle. And from this one, what would be the radius of the circle? Well, from this parametric equation, oh yeah, we're starting at value of 1. So we've already chosen the radius is 1, and x squared plus y squared is equal to r squared. That's the equation of a circle. The radius is 1. And so this hypotenuse is going to be 1, and I can find the x value. The x value right here. Here's the angle. I draw sun-shining rays. That means that this is the sine component. It's shining on that sine component. The other component's the cosine. And so we have this component's going to be the cosine. So I take the hypotenuse and then take it by multiply it by the cosine of t. Anytime you take the hypotenuse multiplied by a sine or cosine, it's going to be a percentage. And we see that it's going to be a percentage between 0 and 100%. So we get that reduced length of the hypotenuse. So it's the hypotenuse. In this case, it's very close to the hypotenuse times 50%. That's what this length is. And so we have the hypotenuse, or the radius of 1, times cosine t. Or instead of just 1 cosine t, it's just cosine t. So that x value is cosine t. And then this y value, if we did the right triangle, is going to be the hypotenuse times sine of this angle t. And we have 1 times sine of t. That's going to be this. And the 1 can just be irrelevant. But that, for doing trigonometry, always, and anytime you see sine and cosine, because I haven't done that lately, as long as it's not squared, but even if it is squared, if you see sine and cosine, put your own 1 out front and just know that kind of represents the hypotenuse. You're taking a hypotenuse of 1 and taking a percentage of it. If you have cosine squared, t, then you have cosine t, and then multiplied by cosine t. So you could even do the first one, be like 1 times cosine is a percentage of that cosine, and then you're using this as your new hypotenuse times the cosine of t. And that's really useful when it comes to learning about the double angle proofs. Okay, so hell yeah. So we're going to be done with this video, unless we sucked at that one. So maybe, how many more examples are there? We could do this next circle one, just because we did horrible on that first one. So what curve is represented by the parametric equation? So I'm going to start at 0, 1, and then I'm going to go around the curve, and then this is going to be time pi is going to be there, and the times are going to be 0, pi, and 2 pi, and I have a dot on 0. And the next dot just shows me 2 pi. But I know that pi has to be a dot in the middle. And so every time I go around, every 1 second, I'm going around a circle. And so what curve is represented by the parametric equations? So x is going to be sine 2t. So at time 0, I'm going to... my x, so this is my x value. I'm going to be 0 at sine of, and then so it would be pi divided by 2. So if this value is pi divided by 2, then I'm at 90 degrees. And does this even show you what direction I'm moving? Because it says we're moving... So let's start with 0, 0. So I'm going to be at x is equal to 0, but at 0, t, I'm going to be at 0, 1. So I can see that. And then heck yeah, as t increases in the positive direction, let's say I am a pi divided by 2, then it would be sine of 90, and I have a value of 1. So if this is sine of 90, my x value is 1. If this is cosine 90, my y value is 0. So that can show you that we're moving in this direction. And then you could do it again. Sine of 180 is 0, so I'm back to 0. Cosine of 180 is negative 1. And so let's, because if I just have some arbitrary angle from the x-axis, and we're doing... 0 angle, I'm going to be at 0, 1, 0, And then if I go up to 90, I'm going to be at 0, 90. So the cosine of 0 angle is 0. The cosine of 90 is 0, but the cosine of 180 is -1. So yeah, so at when this is pi, I'm going to be at -1. So I'm going to be down there. And hell yeah. And then so that's just when this value is at pi. But that's where my t is going to be pi divided by 2. You know what I mean? So then I can kind of see, well, let's go back up to when this is 2 pi, aren't I back up to my starting point? Because if I throw in 0 here, I'm going to be at, again, 0, 1. And if I throw in, if this value is 2 pi, it's going to be 0 as well. If this is 2 pi, it's going to be 1. So I'm back there. But then this interval, so when this is 2 pi, my value t only has to be pi. And so in this says I'm going to do the interval of 0 to 2 pi. So at pi, I've already gone around the circle once. So we have, once I get to pi, I've gone around once. And then once I get to 2 pi, I've gone around twice. So even though we got 3 different points right here, we only go around the circle twice. There's once and there's twice. And so on that interval, we go around the circle twice. Let's see. And so we have to eliminate the parameter, like what's a trigonometric equation? And I think that's the most useful. It's like, what is a trigonometric equation that relates x and y? You know, when x, or what relates sine and cosine? You know what I mean? And so the most obvious one is that if this value is squared, with the same angle right here, and this value is squared, then that's going to equal 1. But this value is x, and this value is y. So x squared plus y squared is equal to this squared plus this squared is equal to 1. And so then here is our equation. So let's read. So the parametric equations, again, represent the unit circle. X squared plus y squared is equal to 1. But as t moves, or t increases from 0 to 2 pi, the point xy is equal to, so the, you know, this point that's represented when time is 0, it's going to be 0, and cosine 2t is going to be 1. As that goes, that starts at 0 to 1 and moves twice around the circle in the clockwise direction in the figure. So, and that's going to be, so this one was on the interval 0 to 2 pi. It moved around once. But then when we, so this makes sense to me, because sometimes learning on your own, you know, when people introduce terms, it's just too fast. And it's just like, I don't believe you, or I think it's too complex. But what this says is this, you can say this is an angle multiplied by a constant. And this constant says, you know, gives you the how many times the thing is spinning. And so that's kind of interesting. And so this one, you know, on this interval, you know, if we say the intervals of the time are going to be the same, this one spins twice, this one spins once. And so, you know, how do we say that? This one has a, and let's say this interval is 1 second. Let's say this interval from 0 to 2 pi is actually 0 to, you know, we'd throw another parameter in here that 2 pi actually represents 1 second. I guess that would change our equations, wouldn't it? But I think I need to do that just for now, just to be like, hey, in 1 second, this thing rotates twice. And then in 1 second, this one rotates once. Because this is related to the frequency. They always say, like, this term, I think, is related to the frequency. And I'm just trying to use my own intuition, and I'm kind of figuring out why that is. And so the frequency is how many times something happens in a second, you know. And I'm sure it has a formal definition, but my examples are I use a light bulb, you know, or AC current is like 60, like a frequency of 60. Every second electricity goes on and off or switches directions 60 times per second, And so light flickers at 60 times per second. So that's 60 things happening in 1 second. This is 2 things happen. That's a frequency of 60. This is 2 things happening in 1 second. So the frequency would be 2. And this is 1 thing happening in 1 second. And so this has a frequency of 2, and this has a frequency of 1. Now, I might have that totally wrong, but this is where you would go like to AI. In sine kt is k the frequency. Yes, and this, you know, if you just have sine is equal to kt, that's also just the angular frequency. It's like how many times, and is that frequency per period, or frequency per half period. Let's see that. Is the angular frequency measured the rate at which the phase of a sinusoidal wave-like changes over time is typically measured in radians per second, the time it takes for 1 complete cycle. So it is a complete cycle, knowing that, you know, circles will kind of hit 2 spots that are similar every cycle. Hell yeah. And does that make sense? Because if you have a sine wave that goes up at a 45, we're going to go up and then down and then up. You know what I mean? And if we were at 0, at halfway around, we're at 0. And so everywhere on a sine wave, there's 2 places that are the same, you know what I mean, that you hit at the same time. But in 1 period, you're going to go through that full cycle. And so the frequency. So hell yeah, I've never even looked that one up, but I think we did it. Okay, so I think I'm done with this video, but it's just like my way of picking up a textbook and learning, you know what I mean, using a little bit of Google, but then really exploring like where your limits are, where my limits are, and then trying to expand upon them. Because if you don't expand upon those limits, then those are going to be your shortcomings. Because especially when you know something over here and then you know something over there, and they're just obviously related, but it's hard to see that. That's where the exploration, you know, is really useful. All right, I'm going to be done with this one. Thanks for joining me, and that's a video.